Welcome to this guide on Cyclic Redundancy Check, or CRC for short. CRC is one of the most widely used error detection methods in digital communications and storage systems. You'll find CRC in Ethernet networks, USB connections, zip files, PNG images, and many more applications. CRC can detect accidental changes to data during transmission or storage. It's a mathematical checksum that catches errors with very high probability. Let's understand how CRC works, starting with how we represent binary data mathematically. The foundation of CRC is treating binary data as polynomials. Consider the binary number 1101. Each bit position corresponds to a power of x. The leftmost bit is position 3, which is x to the power 3. Moving right, we have x squared, x to the power 1, and x to the power 0. A bit value of 1 means that term is present. A bit value of 0 means that term is absent. So 1101 becomes x cubed plus x squared plus 1. The x to the power 1 term is missing because that bit is 0. This polynomial representation allows us to perform mathematical operations on binary data, which is the key to CRC. Let's look at another example. The binary 10011 becomes x to the 4th plus x plus 1. Now that we understand polynomial representation, let's see how CRC uses polynomial division. The CRC algorithm is based on polynomial division. Here's the basic idea. We divide our message polynomial by a special generator polynomial, and the remainder becomes our CRC checksum. The generator polynomial is predetermined and known to both sender and receiver. Common choices include CRC-8, CRC-16, and CRC-32. The division uses XOR instead of regular subtraction. In binary, XOR is the same as addition without carrying. The sender appends the CRC to the message. The receiver divides the entire received data by the generator. If the remainder is 0, no errors were detected. Let's see the polynomial division process step by step. Let's perform a simple polynomial division to understand the process. We'll divide 11010 by the generator 1011. First, we write the dividend with enough zeros appended. We align the divisor with the leftmost one of the dividend, then perform XOR. The XOR result is 0110. We drop leading zeros and bring down the next bits. Now we align the divisor with the new leftmost one, which is at 1100. XOR gives us 0111. We continue with 1110 after bringing down the next bit, aligning again and performing XOR. The result 0101 has fewer bits than our divisor. This means we cannot divide further. The remainder 101 after dropping the leading 0 is our CRC checksum. This gets appended to the original message. Now let's see a complete CRC-8 example. Let's encode a message using CRC-8. Our message is 10110011, which is 8 bits. The CRC-8 generator polynomial is x to the 8 plus x squared plus x plus 1, which in binary is 100000111. Since our generator has 9 bits, we append 8 zeros to the message before division. This gives us space for the CRC. Now we perform the polynomial division. I'll show you the key steps. After completing all the XOR operations, the final remainder is the CRC-8 checksum. The CRC-8 checksum for our message is 11000011. The complete transmitted message is the original data followed by the CRC checksum. Now let's see how the receiver detects errors using this CRC. Let's see how CRC detects transmission errors. When the receiver gets a message with CRC, they divide the entire received data by the same generator polynomial. If the data was transmitted correctly, the remainder will be exactly 0. But if even a single bit was flipped during transmission, the remainder will be non-zero. Let's see a concrete example. Here's our correctly transmitted message. Now imagine bit position 5 gets flipped during transmission. A 0 becomes a 1. When the receiver divides this corrupted data by the generator, they get a non-zero remainder. The error is detected. CRC can detect single-bit errors, double-bit errors, and many other error patterns with very high probability. However, CRC cannot correct errors. It only tells you that something went wrong. The receiver would need to request retransmission. Let's summarize what we've learned. Let's review the key points about CRC. First, CRC treats binary data as polynomials. Each bit position corresponds to a power of x. Second, CRC uses XOR-based polynomial division. The remainder of this division is the checksum. Third, the sender appends the CRC to the message. The receiver verifies by checking if the remainder is 0. Fourth, CRC detects errors with high probability but cannot correct them. Fifth, CRC is used everywhere: Ethernet, USB, zip files, PNG images, and many more. Thank you for watching. You now understand the fundamentals of CRC error detection.